force on a current carrying conductor in a magnetic field. Here's the magnet with its north pole and its south pole. If I bring another magnet close to it, with its south pole towards the north pole and the north pole away, we find there is a force of attraction between these two magnets. These magnets attract each other. However, to the same magnet with its north pole and the south pole, I bring the north pole close to it. Then I find the magnet show a different behavior. They repel from each other. So I can conclude that like poles of magnet repel each other, while unlike poles, they attract each other. So one magnet exerts a force on another magnet. Every magnet is associated with a magnetic field. So magnet 1 has its own magnetic field, and the magnetic field lines are from the north to south direction. This magnet 2 will have its own field, which will also go from the north to the south direction. North to south. These two fields interact with each other, and hence a force is produced. However, in this case, the force is a force of attraction. The same thing would happen in the second case. In magnet 1 will have its own field, magnet 2 also will have its own field, and these two fields interact to produce a force. So here the magnet 1 has its own field, which is from north to south. It's a north to south, and the magnet 2 also has its own field, which is from north to south. Emerge from the north, merge in the south. In this case, since both the like poles are close together, there is a force, but the force is that of repulsion. So when two magnetic fields interact, there is a force produced. We also have learnt, if we have a conductor and there is no current in the conductor, the compass needle remains in the north-south direction. But however, when current begins to flow through the conductor, then immediately the compass deflects from its north-south direction. On passing the current, it deflects. The north is now here, and the compass has deflected from its north-south direction, which means the compass has experienced a force and hence it is deflected. However, if we stop the current passing to the conductor, the magnetic needle returns back to its north-south directions. Let us now explain this phenomena. When there is no current passing to the conductor, there is no magnetic field associated with the conductor. However, there is a magnetic field associated with this compass, because this compass is a magnet and there is a magnetic field associated with it going from the north to south direction. Now when current begins to flow through this conductor, a magnetic field is now produced around this conductor. So now we have two magnetic fields interacting with each other, and because we have two magnetic fields interacting with each other, there is a force produced, and this force pushes the compass away from its north-south direction. So we can say a current carrying conductor exerts a force on a magnet. When a magnet or a compass needle is kept close to a current carrying conductor, the magnetic needle does not remain in the north-south direction. It gets deflected because a force acts on it. Let us ask the reverse question. What would happen if a current carrying conductor is kept in a magnetic field? We'll now answer the question, what will happen if a current carrying conductor is kept in a magnetic field? So if I have a magnetic field, here is a magnetic field, and I have a current carrying conductor kept in this magnetic field. Will the magnetic field exert a force on the conductor? And yes, it does, and we will learn about this force. A magnetic field, this magnetic field will exert a force on this current carrying conductor. So the magnetic field will exert a force on the conductor, just like in this case the conductor, the current carrying conductor exerts a force on the magnet. Here the reverse also happens. The magnet also exerts a force on the conductor. We'll now go ahead and learn about this force exerted by a magnetic field on a conductor. So here we have a magnetic field, and there is a current carrying conductor placed in the magnetic field. Now this current carrying conductor will also have its own magnetic field. So here again we have the same situation. We have two magnetic fields interacting with each other, and if two magnetic fields begin to interact with each other, we will definitely have a force produced. So that's the reason why a magnetic field produces a force, exerts a force on a current carrying conductor. If you remove the current, if the current stops, the force also stops. Because now, if the current has stopped, there is only one field, and that is this magnetic field. There is no field associated with the conductor because the current has stopped. So the force also ceases. There is no force. So this is an arrangement to demonstrate how a force acts on a current carrying conductor. We have AB, conductor AB, through which there is a current flowing through it, because if you see, the conductor is now connected to this battery here. So you have a current flowing to the circuit. And we have this magnet with its north pole and the south pole. And you notice that this conductor AB is kept in this magnetic field, because there is a magnetic field in this magnet from the north to the south. Here we have magnetic field lines from the north to the south. Now when current begins to flow through AB, here is current is flowing, it enters here, the current, then it flows through AB. Now the minute current begins to flow through AB, AB also has its own magnetic field. So we have two magnetic fields, one due to the magnet and the other due to the conductor. So one, the yellow magnetic field, is due to the conductor, and we have the other one that we have marked in green, due to magnet. When both these fields now interact, a force will be produced, and this force will push AB. And hence, whenever we keep this current carrying conductor in a magnetic field, we find that the conductor is pushed, is moved on one side, because it experiences this force. Now to learn the factors on which this force depends, one factor you will definitely agree: if the current in the circuit is increased, if current increases, then this magnetic field will also increase. It will be very dense, the magnetic field. And because the magnetic field will be dense, the force between the two magnetic fields will also increase. So one factor on which it depends is larger the current, greater is the force. Another factor on which it depends is the length of the conductor. A short conductor produces a weaker field, while a long conductor produces a stronger field. So longer is the length of the conductor, greater will be the field, and greater will be the force acting on the conductor. It also depends on the angle between the magnetic field and the conductor. So this is the magnetic field, and in this magnetic field we are now going to place a conductor, and suppose we place this conductor perpendicular. Here is current flowing to the conductor, and the angle between the conductor is perpendicular to the magnetic field. The angle between them is 90. This angle here is 90. The conductor is kept at 90 degrees to the magnetic field. Then we find that the force is maximum. But however, if we keep the conductor parallel, so here is a magnetic field, and in that magnetic field we are placing our conductor, but now we are placing our conductor parallel. The current is moving parallel to the field. So in this case we find there is no force acting. So we have placed conductor, or the current is moving parallel to the magnetic field. Here the force is 0. So the force also depends on the angle, between field and conductor. And to summarize it, if the angle that we call it theta is 90, force is maximum. But theta, that is the angle, is 0, means parallel, then we say force is 0 or minimum. In case here the angle is 90, theta is 90, in this case theta is 0 because it is parallel. So we summarize it out here again. Have you seen in this first case we have theta is 90, the current is perpendicular to the field, and here the current is parallel, so the theta is 0 and the force becomes 0. Now every force has got a magnitude and direction. Earlier we have discussed the magnitude of this force, and we saw that it depends on 3 factors. The current to the conductor, greater is the current, more is the force. We also have seen that it depends on the length of the conductor. Longer conductors produce a greater force, and we saw the third factor was the angle between the magnetic field and the conductor. So that goes for the magnitude of the force. What about its direction? Here we will learn the direction of the force. Now the direction of the force is given by Fleming's left hand rule. And it says, stretch the thumb, the forefinger and the middle finger of your left hand mutually perpendicular. So in this diagram you can see, this is the left hand, the thumb, the forefinger and the middle finger are held mutually perpendicular to each other. If the forefinger points to the direction of the magnetic field, so here is the forefinger, and sees the magnetic field is in this direction, north to south, and the forefinger is pointing to the direction of the field. Then we have the middle finger in the direction of the current. So here the current is acting downwards, so the middle finger is acting downwards. Then the thumb will point the direction of the force. So here we have the thumb which is pointing upwards, hence the force would be upwards. So here we'll have again the magnetic field, but now we are going to reverse the direction of the current. The magnetic field remains the same from the north to the south, but the current now we are going to reverse it. Here's a conductor, and now the current is going in the upward direction. So the field is here in this direction. The current, however, is in the upward direction. So the force, you will agree, will be perpendicular. So the force will be in the downward direction. So if you reverse the current, the force also is reversed. However, if you keep the current the same, and now I'm reversing the field. See, I put the field here was from towards my right, now the field is towards my left, and the conductor, the current to the conductor is the same, it is going downwards. Again, here too you will find that the field, the force also begins to act downwards. Here too in the second case, I'm keeping the field the same as this case here. In the first case, I keep the field same. Here we need to reverse the field. So here we are reversing the field. However, the current I'm keeping the same. The current is flowing upwards. Just like here, current is flowing upwards. Here too, current is flowing upwards. Here the force was acting downwards. Here the force will act upwards. So if you reverse any one, if you reverse the magnetic field, the force gets reversed. If you reverse the current also, the force gets reversed. So the direction of this force will depend on two things: on direction of field. You reverse the field, the force gets reversed, and on the direction of the current. You reverse the current, the field or the force also gets reversed. To summarize what we have learnt, we have learnt a magnetic field produces a force on a current carrying conductor. So if we have a magnetic field here like this, and we have a current carrying conductor placed in it, a force is produced. See also the magnetic force depends on three factors, and the factors are current in the conductor, stronger current, more force. It depends on length of conductor, longer conductor, more force, and it depends the angle between the conductor and field, which means the angle is 90. We saw the force was maximum, and when the angle was 0, the force was minimum. We also saw that the direction of the force depends again on two factors. One was direction of the field. You reverse the magnetic field, the force is reversed. It also depends on direction of current. Reverse the current, the force also reverses.